Hello and welcome. My name's Alnez, and this is the final project for real analysis with Dr. Garcia. Today, the two questions that I will be attempting and proving is question 94 and question 99. Let's begin. Find a topology for R, the real numbers, and a sequence that only converges to 1 and 2. Okay. I guess let's begin with this. Let's let well, let's let some topology tau be a topology. On the real number sets, which would be defined by so in other words, let's let the open sets in the topology be the empty set, the real number sets, and the closed set, or the closed interval containing 1 and 2. So, let's also consider that all open sets in the standard topology of R don't contain 1 and 2. Now from this, let's consider a sequence, I don't know, some random variable x of n. Seriously, talking and writing, two different things, is pretty tough. I think I mentioned this in the previous video I made. But yeah, let's consider the sequence x of n in the real number sets, defined by x of n equal to 1. This of course would imply that every open set that contains 1 would also contain all of x of n. Denoted as the limit as n goes to infinity. X of n would be equal to 1 such that it converges to 1. And the same thing could be said for every open set that contains 2. The same holds true. So let's suppose that every open set that contains 2 would contain x of n. My bad. X of n such that the limit as n goes to infinity, x of n would be equal to 2. I did not give myself enough room. Let's erase real quick. Let's erase this right here. I'll just reiterate right now. So the two things we have is the limit as n goes to infinity for every open set that contains, oh, wrong one. For every open set that contains 1, x of n would be equal to 1. And for every open set that contains 2, the limit is n goes to infinity, x of n would be equal to 2. These are the two main ideas we have so far. So, of course, let's consider, let's let actually some x be an element of both the real number sets and the closed interval from 1 to 2. So let's also now consider an open set containing x itself that would also be an open set in the standard topology of R. Of course, with it being in the standard topology isn't the condition we need exactly, but we need it to both be in the standard topology, and also we need it to not contain one and 2. So we need both these conditions to be true, and if that were to be the case, then this would imply that the open set does not contain any limit as n goes to infinity. Any limit as n goes to infinity, which of course would then imply that x, denoted as an element of the real numbers and the closed interval from 1 to 2, is not a limit of x of n. Therefore, both 1 and 2 would be the only limits limit points of x of n. Alrighty, let's move on to question 99. If a sequence flirts, a subsequence does not necessarily flirt. So let's consider, well, let me zoom in. Don't want to not have enough space like last time. Let's consider, well, might not need that much space, but alrighty. Let's consider some sequence x of n where it will always be 1 if n is even, and it will always be 1 over n if n is odd. So it would be denoted as 1, comma, 1/2, comma, 1, 1/5, 1, so on and so forth, for all eternity. So this sequence x of n is flirting, or rather, yeah, is a flirting sequence sub n with x equal to 0 specifically. Considering its interior, x sub 2n, this would be equal to the sequence x sub 2, x sub 4, x sub 6, you know the drill, I'm sure. Notice how all the n's are even. This would of course translate to 1, 1, 1, 1, yada yada yada. There we go. This would mean, though, unfortunately, or rather fortunately, because what we're trying to find, we want to say that the subsequence itself, this inside sequence, is a subsequence of x of n with these conditions. Notice how it really doesn't flirt. With the sequence therefore, we could say that if the sequence of n flirts, as noted with the first example, the subsequence, in this case x sub 2n, doesn't necessarily flirt.